All right, so we're talking about some part in chapter 2 last time, so I'll try to just review real quick and then move on to the next topic. So we talked about the acid and base. What about those? So mainly we had two types of definition we can try. The first one is Bronsted-Lowry, right? Remember? Bronsted-Lowry. Okay. And then you can also use the Lewis acid and base too. But like I said before, most of the time we're going to use this one. This might be just fine to work with most of the case. But maybe some special case, we're going to use the Lewis acid and base definition. So we can talk this a little later. But obviously what it really means is if it donates the protons. So there's one thing I can say. Hydrogen cation here because this is actually something I didn't mention last time. It's because of the water. So whenever you have the HCl, strong acidic solution here, you can also do, if you can see that, so you can do this one. This is the alkaneous one. This is the Bronsted-Lowry. So you can have. So you can consider hydrogen cation as same as hydrogen cation. So this the only thing you have to know is this is meaning your protons. Okay? So if it donates protons, this acid, if it accepts or still protons, then that's base. Okay? This is base, this is acid. This is what we did at the last part of was Friday, right? Friday. Okay. And then the Lewis one is the vice versa. The acid will actually accept a pair of electrons instead of donating the proton. It's pretty much the same job. Anyway, a base now would donate the pair of electron to some of the things. So they're just using either protons or electrons, but they're meaning the opposite charge. So you can define those two in a two different way. But this is more a broad, bigger, like a concept of acid and base. But we still we still be quite happy with this one. Maybe about like 90% cases of the organic chemical reactions. Anyway, okay. Makes sense, right? It's just a quick review. Okay. So how are you gonna use this one? Okay. How are you going to use this information real quick? So once again, last time we talked about the Ka, right? Ka. Okay. If the K is higher, means this one. Stronger acid here. So ironically speaking, if we mean by stronger acid, it's only possible for the weak acid. Because the strong acid, it will always give you almost what? 100% dissociation of your protons. So for example, if you have HCl, it's quite strong. If you have a 1 mole of HCl, you can almost predict either hydrogen cation, doesn't matter, hydrogen cation, you're also going to have 1 moles of those two donated into the system. This is a strong acid here. But ironically speaking, once again, K is only for weak acid. Because they're not going to do the full dissociation, but partial dissociation. So how much of their original form would dissociate into form of the proton and the one without the proton? That is the Ka means. Makes sense, right? This is the review. So if you have a high K means you're going to have a more of this one over its original form. So obviously it means a strong acid, but it's only possible for weak acid, meaning it's actually a kind of relative term. That's why I say it's not strong acid, but stronger acid. Makes sense, right? So if that is the case, just one thing, if you think about the pKa here, I hope you guys remember, if this is a higher Ka, the p value here is once again negative log of something. But this is a negative law. So if this is high number in Ka, this number will be lower or higher?
Lower.
Perfectly. So the lower pKa actually means higher Ka means it's stronger acid. So if you have a high number for pKa, it actually means weaker acid than something, or substitute relative term. So you're going to compare these two. So this is the last part of the Friday lecture. I'm going to do this because I'm going to show you the practical problem now, how we're going to solve the problem. And I'll show you how to use this one. Over here. So if you have acetylene over here, so this is interacting with the OH minus. Okay, so I hope you guys remember this one from the previous lecture. I put the negative charge on here, but not on the hydrogen, but on the oxygen, because oxygen is more electronegative. So if you have to put the extra electron on here to make it formal charge -1, this oxygen should be the better one to possess that negative, additional electron. Makes sense, right? So if that is the case, think about it. So I didn't show you here in detail, but what it really means is this one. So if you look at this one here and there, hydrogen is group 1, so it only has 1 electron. It's totally fine with it. And there's another one for the oxygen here, but I put the negative charge, meaning I didn't tell you here, but you need to know that already there are 3 implied lone pair there. Because if you have a 3 lone pair here, you have a 1, 2, 3, 4, 5, 6, 7 instead of 6, because this is a group 6 element. So this is why this one will have a 1 more extra electron. That's why it carries overall negative charge. You see that, right? So even though I don't show you on the exam, I kind of assume that you guys already know this. Okay, perfect. Anyway, it was like, so I'm just gonna write this one here. It doesn't matter if I put here, you still assume this is on here, okay? So if that is the case, they're gonna interact with these two, and then they're going to make the acetylene anion and water. Okay? So obviously this part made this one. Okay, now it goes to this one, goes to over here. So here, if you look at this one, if you remind about what you just think about the Bronsted loaded acid and base, this is the one that donated proton to this one, right? Hydrogen anion here. So this is acid here, because it donated the hydrogen cation, okay? Proton. And this is now accepting the hydrogen cation to themselves. So we define this one as base. Okay, this is the case. So here's the thing. Whenever this one donates the protons, now it has the one without the proton now, right? So meaning, if you think about this one, this is what we call conjugate base. Meaning, this, like I said, this is the weak acid. So it's not dominant in one direction at all. So you always need to think about in both way, forward and reverse directions. Okay, and you're gonna find out which one is more dominant in this both direction over here. So you're going to see this one over here. This is conjugate base. So if it's going on opposite directions, because we always think that is goes from the left to the right, but sometimes you have to think about there might be the reverse direction from right to the left. So if this one goes to that side, if this one to be its original form, they need to accept the proton. This is the one without the proton. But if they go in the reverse direction, they need to take the proton. So it kind of works as base, but on the other side. So this is why we call this conjugate base. Okay, the same thing over here. We have a water over here, but if water to be hydroxide anion, it has to donate the proton. So they can be in original form, which is hydrogen anion. So this is conjugate, don't need the proton, right? It's conjugate acid here. Makes sense, right? Okay. So once it's acid and base, and the other side is totally different one, but conjugate base and conjugate acid here. So if this is the case, this is what we wanted to know about the pKa. So if you think about the pKa of the acetylene over here is about 25. Okay? This is about 25. And if you look at the water, which is also your conjugate acid on the other side, this pKa about the water is about 15.74. So once again, you need to compare these two numbers. And this is a pKa 25, this is 15. So this is a lower number here on the right side. So you can actually assume that in the forward and reverse directions, you can assume, oh, this is relatively speaking, right? Relatively speaking, water is stronger acid than acetylene by just looking at the number. So I know this goes on to the both way. It can go also both way, but this will be more dominant than the other because it's stronger acid there. So, oh, just one more quick. So if this is a negative charge in this carbon, because there's a lone pair, but I'm not gonna show you because you probably know already this one. This is group 4, but it has 1, 2, 3, 4, 5. This is negative. Anyway, so this is why. This is how we can use those numbers for pKa or the both side, and we're gonna find that they go the both way, but this is not so much, but a lot on the reverse direction here. So you can actually predict where this direction shifts in the which directions. Is it going to the left to the right or right to the left? Just simply looking at the numbers for pKa. Makes sense, right? Do you have any questions?
So the lower or the higher value means it's weighted towards that side.
Lower to the higher. pKa, like you're correct, yes. Lower to the higher.
Which one means it's weighted to that side, the lower value or the higher value? Okay. Is it weighted towards the 15 side or the 25 side? I'm just not clear on that.
So the pKa value will tell you the relative term of the acidity, right? So if this is where you can find the lower one that has a stronger acid, right? So if that is stronger acid than this one, they're gonna play more role on to right to the left.
Okay.
So this is why you're gonna see this
Okay.
actually
So the higher value means it's weighted towards that side. Okay.
Yeah, it's a relatively speaking. Perfect. Yeah. Any other questions? Again? Alrighty, so this is, I'm not gonna lie, I'm gonna put this on the exam, okay? So please remember this one. Very similar question will be on the exam, very similar one. So you can try to, but simply, the only thing you really need to remember is what the number in pK really means in your reaction at the going forward and reverse reaction at the same time, okay? It will tell you the relative terms of the strengths of the acidity, and you can tell which way will be more dominant in other direction. Okay. All right. So the next part is actually this is the last part of the chapter 2. So this is what we call intermolecular force. You guys have probably already heard this one. I think Jenkins 2, right? Jenkins 2. So intermolecular force, simply what it really says in this term already here. So inter means between something. So if you think about the international airport, you're always thinking about going to the other country, right? So that is also something about between. But it says molecular, so it's between molecules. Because the intermolecular means there's something between molecules. And there's force, meaning there are going to be some force interactions. So whenever they do some type of interaction, we can measure the strength of the interaction is force. Okay? So we're gonna talk about the force or interaction between molecules, and that's how you can define the intermolecular force. So whenever you think about the intermolecular force, you have to think about at least more than one molecule, because there's no intermolecular force among the one molecule is impossible. So anyway, if that is the case, the one thing you have to know is what we discussed before, dipole moments, right? So if you have some polar covalent bond, some type of different electronegative elements, or kind of make it covalent bonds, they'll give you some type of moments in the covalent bonds. They can make some electropotential difference in the different side of the molecule here. So if that is the case, you can think about some molecules like made of maybe A and B elements over here. Okay? If that is the case, you can think about, I'll give you just one example here. Okay? If you have something looks like this one over here, you can kind of consider this is like a whole structure. There'll be a little more, but think about, anyway, I'll just make it more simpler form. In this case, the fluorine is obviously what? More, I can switch to even chlorine or fluorine, doesn't matter, but if this is more electronegative elements over here than carbon here, meaning, I hope you guys remember this one, the electric density by chance will be more on this side, right? So they're not having a clear separation of the numbers of electrons there, meaning formal charge, okay? But what we're just talking about the very slight change. So meaning it's a slightly negative charge on this side of the molecule. This side of the molecule will be slightly positive, meaning relatively speaking. Because of the difference in electronegativity, each different element will have different strengths of the pulling the electron towards themselves by chance. Okay? So this is why this will have a certain type of dipole moments, like a polarity there. So if that is the case, once again, you're going to have another molecule next to it. Because it's about the between molecules, not just one. So I'm going to draw another one over here. And then you're also going to see this is slightly positive. This is slightly negative over here. Okay? So if you think about this one, it doesn't have a really big change in the formal charge, but just slightly different electropotential change over the whole molecular structure. So if you have a slightly positive charge, slightly negative charge, they're going to have certain interactions there, right? Because it's slightly negative, so it's not really strong interaction, but very somewhat okay, but small interaction between these polar molecules. We call this dipole, because dipole moments, right? Dipole, and this is another dipole, right? So dipole interaction. Interaction. Okay, so this will make somewhat quite strong interaction, meaning they're gonna maybe kind of tightly bond somewhat in a certain amount of the strengths. Okay, so this is what we call dipole interactions over here. This is important to understand in organic chemistry because you're gonna see a lot of organic compounds bound to a lot of different elements, and they make some type of polarity of the compound. They may do very different in the physical property, especially in your second experiments. Most of you done with the first one, right? Okay. The second experiment you're gonna do more on this one. So anyway, sorry. This is the something you can do about intermolecular, the dipole interaction here. So we have a kind of a special case of dipole interaction is what we call hydrogen bond. Okay. Some just call this H bond, hydrogen bond. So hydrogen bond is also dipole interaction, but special one. That's why we named it with the special names of hydrogen bond. So if I say interaction means there's a certain force between molecules, but not so strong. It's not so strong. But we call this hydrogen bond, right? So bond is much more stronger form for the bonding. So meaning bond means it's really strong interaction. So if I call something interactions or force, means it's their interaction, but not as strong as what we can call bond. But we call this one hydrogen bond because this is special, because this is the strongest possible dipole-dipole interaction. It could be as strong as it can be called bond. Okay? So meaning hydrogen bond is the strongest one, strongest dipole-dipole interaction. So we kind of specify, they're calling it as a like hydrogen bond. Okay? So why this so special is here. Okay, why this so special? Hydrogen bond is special because it is much stronger than other regular dipole-dipole interaction because of this. If you think about the hydrogen over here, this hydrogen, if you look at the hydrogen on the periodic table, obviously it's very small, right? This is very small. And electronegativity wise, it's also relatively quite low too. But if this hydrogen is interacting with the one that has the either oxygen or fluorine or nitrogen, if you look at the oxygen, fluorine, and nitrogen on the periodic table over there, you'll find those elements on the very top, second period, and also the right side of your periodic table. Meaning they all are really highly electronegative. They're very high numbers in the Pauling unit. So, and also they're also quite small elements as well. So the interaction between this is small hydrogen and the gap between these two is quite a lot in electronegativity scale. So interaction is a lot stronger than other dipole-dipole interactions. So this can be like as strong as like a bond, type of a bond. So we call this the hydrogen bond. That's why. But just one more thing that I kind of want you to remember is this type of case. So if I give you this one, okay? Oh, yeah, it should be. So this one and this one, okay? So once again, this part will be slightly negative. This is slightly positive, right? Because of the carbon, hydrogen, and fluorine over here. So there will be interaction between these two. Like I said here, hydrogen to fluorine, hydrogen to the fluorine. But this is not hydrogen bond because the to make the hydrogen bond, the hydrogen has to make covalent bond to either oxygen, fluorine, nitrogen like water, and also intermolecularly speaking, interacting with one of those three elements as well. So water would be a good example. Like water is the hydrogen where you make a covalent bond to the oxygen, and also with other water molecule, you can interact with the oxygen side of the water. But this one, they do have an interaction between hydrogen and fluorine, but this hydrogen is bound to carbon, and this fluorine is bound to carbon as well. So this is just one of the dipole-dipole interaction, but it's not a hydrogen bond.
So that's a dipole interaction, but it's not an H bond?
No H bond.
Okay.
Perfect. Very good. This is kind of a bit tricky, but this is something that I want you to kind of remember. Makes sense, right? Very good. Okay, so now we talked about the dipole-dipole interaction, and we know there's a hydrogen bond. And then, what about if there's no polar molecules at all? So we only talked about the non-polar molecules. Okay. There's no polarity on the compounds. What happened to this one? Interestingly, even the molecules without any polarity still can interact with each other. But obviously this one will be the weakest one. Okay, this is somewhat strong, quite strong, but this is the weakest version of interaction. because it's non-polar interaction, we call this London dispersion force. Okay, this is also one type of van der Waals, but most usually it's random dispersion force. So here's the thing: if you have the molecule that made of A and B, which will be different different elements, so there will be different electronegativity. So this will have some polarity there for sure. But if you have same elements make a bond all the way, meaning it's the same elements, so there will be no change in electronegativity, right? So this will become nonpolar. And I can say that if you divide in half and a half, you're going to have an equal amount of chance to find the electron near this A, you can say A prime, or this A is the same. So this will have no polarity over here, but this is kind of weird that even though it's a 50-50, this is quite important to understand why it's by chance. Because if it's a 50% and 50% over here, it doesn't mean that you're always going to find the one electron here, one electron here. It just means by chance, you may have an electron over here, one most of the time, but you never know. You have maybe 2 electron charge more on this side at certain short period of time. It is still possible. Because we only did it by chance, we didn't locate the electron. So for instant time, very short period of time, they may have a slight polarity there because of the unpredicted motion of the electron in the molecules. So A and A prime, which is the same elements, but still they might be slightly like negative and slightly positive, relatively speaking, and they may have very small interaction still, but very weak, and for a very short period of time, because we kind of understand the electron as like in a standing wave, and try to apply this wave function to find the 3D map of finding the electrons, but we can have certain time that it's become slightly polar, so there should be some very small interaction. We call this London dispersion force. So this will be the weakest one for sure. Right? Okay. So looks good. Makes sense, right? Again. Perfect. Okay, that's good. So the one tricky example I can give you might be this one. So if you have this is really big common example here. Can you guess if this is non-polar or polar? So this is the one that has polar covalent bonds, but not polar on molecule. Because if you look at this one over here, there are 2 double bonds between central carbon and 2 surrounding oxygen. If you just circle this one over here, it already has 4 electrons around the carbon here. So this is okay. And this one, I will not show you, but you know there will be 2 lone pair already there to make this 2 neutral, because this double bond has 1, 2, okay? And then there'll be 3 and 4 and 5, 6. So it also become neutral as well on both sides. Okay? But this is kind of tricky. That we know there are only going to be 2 double bond from the central carbon. So if you do the polar bond dipole moments on vector sum, it will be still 0 because it's cancelled on the both sides. So this is carbon dioxide is a very good example of the molecule that has polar covalent bond, but still non-polar molecule. Makes sense, right? Because even though we do know there's a electronegativity difference in carbon and oxygen, so you can have some dipole moments from here and here, because of their structure, it actually kind of cancels out on the right. I'm sorry, on the right and the left. So if you sum that vector of the dipole moment, it will be 0. So it still become non-molecular. So if I give you some carbon dioxide intermolecular force, you need to tell me it's the London dispersion force might be the best one to describe. So this is a kind of famous example you also may see on the exam, so please remember this one. Okay? So even though the so the key point here is I showed you if you have a compound made of different elements, they will have a polarity for sure, because they don't have the same electronegativity, because this is a chemical identity of themselves. But sometimes, because of the structure, those dipole moments can be cancelled. So if it be nonpolar, then the intermolecular force among those one with even different molecule, different elements may have no polarity there. Most of the time they will, but like carbon dioxide, we're not sure much of polarity because of structure. Makes sense, right? Yeah. So maybe I can give you one more example. Maybe you can tell me. So you have give you this one. I just showed you this has a polar, right? Because of this one and this one and this one, they're all different, right? How about if I change this all to chlorine? Is this one has polarity or not? No, perfect. Perfect. Because it's a tetrahedral structure, right? But the difference between quite well kind of evens out on all three displays. Perfect. So we're not sure much of the polarity much there. It's a non-polar. Perfect. That's really good. So even though there's the polar molecular covalent bonds, it may still have no polarity over whole the molecule because of the structure. Makes sense, right? Alrighty. So we're done with the chapter 2 finally. So we'll get to I'll try to cover like slightly over the first part of the chapter 3, but I'll promise you do it again on Friday, because we only have 5 minutes, because we need to save it for 10 minutes for the extra credit chance. So anyway, so the chapter 3 is mainly about the arcane. So the R simply means any like a hydrogen carbon sort of a compounds, like organic compounds. But A&E means they're all going to make a single bond. There will be no double or triple bond between carbons, okay? Only single bond between carbons, okay? Carbon and carbon, okay? So those are the ones that we call arcane, okay? So the first part of the chapter 3 is the obviously nomenclature. How are we gonna name this arcane here, okay? So like I said before, you don't have to know about the more than 10 carbons. Like you don't have to know the undecyne, dodecyne, icosane, or even further turquoisane. You don't have to know. But only 1 to the 10, that's good for the exam, okay? You don't have to know about the even higher 20, 30, 40 is okay. So anyway, so we're gonna start with the meth. F, okay, prop, and but, pent, hex, hept, oct, non, and dic. Okay, so this is all you have to know for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is all you have to know. Okay. So this is for your base of the nomenclature. So in a big categories of the compound's name, you have a locant, and you have a prefix, you have a base, and you have a suffix. Okay. So local simply means you locating where your prefix are. Okay. So I'm gonna tell you what prefix is, but anyway. So this is the local means this is information about the where your prefix are, and prefix is like any groups that attach to your base. Actually, I should go the other. I'm sorry, but the base actually means your carbon chain, longest possible carbon chain is your base, like your fundamental base, like a platform to make attaching all the groups and everything. So this is your base. It will indicate how many carbons in your longest possible carbon chain in your compounds. Okay, so that is your base. So if there is any group attached to the base, that is a prefix. And when you attach the prefix to the base, you wanna indicate where that prefix attached to. So that is local there. Okay. And the suffix here is very easy. It's just the ANE, because we're gonna talk about the arcane only in chapter 3, which is all single bond. So suffix for this chapter will be just ANE for whole time in chapter 3. So ANE, you know what suffix means, right? Suffix is like your surname, your family name. So whenever you think about the structure of your nomenclature of the organic compound, this is the most important thing. So whenever you have other functional groups or double bond or triple bond, this is the way you're going to change the part of your name, which is in the last one. So the last part of your name is the most important part of your organic compound. Okay, but those are ones are only. So this is quite important. They're somehow okay important, but this is the important part of your name, like your family name. I don't know if you can change your first name. Can you change your last name too, if you want? Really? Oh. I think that's just. But anyway, obviously you think that your family name is more important anyway, right? Same goes with the organic compound. So I'll do this again Friday. So let's try to have some time for